Now, if you're following along this course and you're interested in Deno, you've most likely have some experience with Node. And most of the time, things like Node and Deno are used for backend, for building servers. Yes, we can do general scripting. We can write all sorts of programs and run our JavaScript code anywhere. But most of the time, and most jobs, are in the backend world, where we build servers to build web apps, to build RESTful APIs, to build mobile apps. But in order to truly understand what we're going to build throughout the course when we build our final project, we need to get a bit of a history lesson in the backend technology. You see, at the end of the day, when it comes to the web and web applications, and even mobile, there's usually this idea of a client and a server, front end and back end. The front end is the browser or your mobile phone. What it sees on the display, that's the client. That's the visual part of things. The back end, though, is what the user doesn't see. When I go to google.com, what I'm doing essentially is telling the browser, hey browser, go find google.com. And it's going to go find where Google has their servers, and it's going to say, hey, can you give me data? Can you give me your Google information? Maybe the Google logo, maybe the search bar. And Google servers is going to receive that and say, oh yeah, here it is. Here's my data. Using HTTP and HTTPS, we're going to communicate and say, here you go. You can have this data. And usually we can have static files like JavaScript, HTML, and CSS files. They're static because, well, these things are written ahead of time and we just send them, they don't change. But let's say a user logs into Facebook. Now it goes back to the server and logs in as Andre. It tells the server, hey, I just logged in as Andre. Can you load up my friends and my newsfeed? And the server is going to say, yep, no problem. Here it is. And it's going to send the client some data. So that's what the backend is. The backend is feeding the information, the data that the browser needs, that the client needs to load up something for the user, something useful. Now, the world of backend can be written, well, in anything, right? A server is simply a computer that does some logic, usually serves some data, serves some files. So our backend can be written in Node using libraries like Express. We can write it in Java, C#, PHP, Ruby, Golang, Python, Haskell, Erlang, even Rust. We can write our servers in any language that we want. And now we can add Deno to this list. But we have so many options, and what you write your backend code with is up to you, whatever makes you productive. But I do want to talk a little bit about the history and why we have this ability to write JavaScript on the backend. Initially, back in the day, let's say 2000s, early 2000s, we had languages like PHP, and we still have PHP, and the model has changed now, but in the early 2000s, most servers were written on PHP. And what would happen is we would get a request from a user's browser, and we usually had a server using what we called usually an Apache web server. So it was a software called Apache Web Server that would just serve HTML and CSS files. And whenever a user needed data, Apache created a separate process for each request. So another user requests the data at the same time. Well, let's create another process. And then another user at the same time requests the data. Well, let's create another process. And Apache created these processes, and the PHP files would run, that was on the disk on the server, on each of these processes. So each request, so each user had a process. The good thing was that this was very simple. Each user had its own process and can run code in its own area. But the problem was if we had multiple concurrent users, that is, if we had, let's say, 50,000 people at the same time asking for data on a server on something like, let's say, Facebook or Instagram that gets a lot of concurrent requests, well, this server is going to crash pretty fast. So in 2009, Node became really popular because of this idea of I/O that we've talked about. The libuv, where it did non-blocking I/O, how Deno has the Tokyo asynchronous I/O. Well, in 2009, Node came along and said, well, let's do this. We'll receive a request. Hey, can you give me your data? And let's say we have multiple concurrent requests. Well, in this case, the Node server, instead of creating a process for each request, simply takes into the JavaScript engine, because it's single-threaded, it's going to take and say, all right, I have a request. I'm going to pass it on to the event queue, to the non-blocking I/O. So it passes it on to something like libuv, or in Deno's case, Tokyo, and passes it on to a thread pool. So it was all in a single process. And whenever something was done, it would come back to the JavaScript single thread and then return the response. So this way, it was never blocking the server. Now, the PHP model worked quite well, but for these concurrent connections, multiple connections at the same time, this I/O model worked really well. The Node model and the Deno model work well when your main performance problem is this input-output. As long as we're able to pass these tasks to the thread pool, then we're great. So Deno piggybacks on this same principle, and this non-blocking I/O principle of backend is heavily used everywhere now. But Deno is able to piggyback off of Node's success, still use the same model, but include those newer features that we've been talking about throughout the course. But enough chatter, let's start building our backend with Deno and see how fun that is.
Hello! And welcome to our final backend project. We're going to be building an API, putting together everything that we've learned into a real full-stack website. But before we jump into coding, let's try to get a bird's eye view of the Deno ecosystem. There are a few different API frameworks that are currently trying to get some traction. And it's early days for Deno, so it's good to be aware of all of them, because technology changes quickly, and Deno is evolving as we speak. Now, all of the API frameworks that we're going to be talking about are available as third-party modules on the deno.land site, and I'll be posting links to all of them after this video. We start with Drash, or Drash. This is quite a fully featured framework inspired by Python's Flask, PHP's Laravel, and another PHP framework, Tonic. It's a top 3 player if we're counting by current GitHub stars. Currently it has 391, and it's very focused on REST patterns. Now, REST is something we'll be talking about more as we go on, but it's basically a way of calling an API and doing create, read, update, and delete functions, or so-called CRUD operations, using the HTTP methods, post, get, put, and delete. REST is basically mapping this HTTP protocol that the web is built on to a standard way of talking to collections of data. We'll be talking about this more as we build out our API, so don't worry if you're still hungry to learn more. Now that we've got a bit of theory out of the way, let's take a look at some Drash code. The thing that stands out most is that Drash uses classes very heavily to represent each resource or endpoint. We define these methods on the class for each of the HTTP methods that we want to support. So in this case, we're supporting get on this / endpoint. Okay, well, now that we've got a taste, let's move on to the next one and see what we're comparing against. Next up, we have Deno Express. Now, this one aims to be as similar to Express as possible. And looking at the code, it looks nearly identical. We can see we define our app, we have some middleware, and then we define our routes by passing in this request and response object. However, if we dig a little deeper and look at this module that contains all of the code, we can see that the entire project doesn't have too many features. In fact, the entire thing is just under 400 lines of code currently. Still a long way to go from an Express replacement. Next up, we have Pogo. It kind of rolls off the tongue. Pogo has some interesting things to offer. It's inspired by the Happy framework, which is another very successful Node.js framework originally created by Walmart. Now, one of the interesting things that Pogo supports, if we scroll down, we can see first of all that it's designed to encourage reliable and testable applications. Routes are pure functions. It responds with automatic JSON, and it has built-in support for React and JSX. Let's see what that means. If you're not familiar with React, JSX is a shorthand syntax for JavaScript that looks like HTML, kind of like this. You can think of it as a really, really powerful templating engine that allows you to mix JavaScript and HTML in your code seamlessly. This can be really useful when doing server-side rendering. And server-side rendering is a technique used for performance and search engine optimization, where we render a normally client-side page on the server and send back the fully rendered page to the client, so the client has to do less work. This generally means that the search engine crawler, for example, the little Google robot that's looking at your page and deciding whether it's ranked highly or not, needs to render the JavaScript code. This can impact the ranking of your site. And the other thing is, if the page is being rendered on the server side, then it doesn't need to be rendered on the client side, which means that that first page load is going to be much quicker because the page has already been loaded. I see a lot of potential for Deno being used in server-side rendering. Speaking of server-side rendering, we have Servest. Servest is currently tied for second in terms of adoption, and it has some great examples here on React integration. This really shows off Deno's browser compatibility and compliance to browser standards, which makes things like server-side rendering much easier to support. One of the other things with Servest is that it's built from the ground up. What I mean is, it re-implements the HTTP server it uses and doesn't use the one that Deno provides out of the box. This gives them a lot of control to optimize things based on their own needs, if they so choose. Now, Servest has been around since March of 2019, which makes it a grandparent in Deno years. This is a big benefit because it's bound to be one of the most mature frameworks. Definitely keep an eye out for this one. Finally, we have Oak, which is a middleware framework for Deno's HTTP server, including a router middleware. Oak should be extremely familiar if you know Express, the most widely adopted framework for Node. And it's nearly identical to Koa, which is the follow-up framework for Node.js from the original creator of Express. He made this framework to better leverage modern JavaScript features, like native promises and async await. I see a bit of a parallel with Deno in this regard, where Deno was created to solve some regrets that Ryan Dahl had with Node. Koa was created to solve some problems that TJ Holowaychuk had with Express. Koa's design goals were to be more modular than Express, making it easy to design middleware that could be shared between projects, and to be promise-based as opposed to using callback functions, like Express, where a callback function is passed into another asynchronous function, and the callback function is called when the asynchronous function completes or is triggered, in this case by a request to this route. Now, Oak took the things we learned from Koa and brought them over to Deno. It makes heavy use of async await and is very unopinionated, much in the same way that Deno is. It's a match made in heaven. And as of the recording of this video, Oak is the clear winner in terms of adoption by a large distance. It has 1,500 stars on GitHub currently. And because of all those reasons, it's the framework we'll be using in this course. All right. Now I know we just covered a lot of different frameworks and a lot of different topics. Don't worry if not everything made sense. The important thing is, now you've had a taste of a few different major players in the Deno framework ecosystem. We'll be diving into Oak in great detail, and once we've become experts in Oak, we can use that as a foundation for getting familiar with these other frameworks, and that'll be a lot easier. Okay, on we go! Welcome back. This is the exciting part. We're starting to build our NASA mission control backend. We start with a fresh Git repository and an empty folder, except for this basic README. Let's start making use of our framework, Oak. I've used Oak's Node.js twin brother, Koa, on a few different large-scale sites, some of which brought in millions of dollars of revenue per day. I know Koa worked great in Node, but it's set up to work even better with the list of game changers that Deno provides. We won't regret our choice. Let's dive into some Oak. We start by creating a file, mod.ts, and making an import. So we're going to import something from our Oak library. And we're pointing to the redirect provided by the deno.land site. Remember how deno.land/x is just a redirect to the source code, in Oak's case hosted on GitHub. But now that we have our import, we're going to do something different. We're going to point our import to a specific version of Oak. You see, different versions of Oak are tagged with specific versions of Deno. So we want to make sure that the version of Deno that we're using matches the version of Oak that we have imported. In our case, we'll be using Oak version 5. So we're going to tag it by writing at v5.0.0. When we version things this way, we're telling the Deno module system, only download the Oak module that's tagged as version 5.0.0. Remember, our import is just a URL, so it's up to the server behind that URL, in this case deno.land, what to send back to us. The version number here is just a label, and we can browse to this URL in the browser. So I'll take it here, and we can see it points to the source code of the latest version of Oak as of this recording. Now, we're going to create an application. So we're going to start by importing application from Oak. An application is a TypeScript class. So we're going to assign it to a variable app, and we're going to construct a new instance of it. The application class has two methods. One is the listen method, which we'll call on our app object. So we'll call app.listen. And we're going to assign a new variable called port, which is going to be the HTTP port that our server listens on. We'll assign that to 8000, And then we'll pass this in to the listen function with this port parameter. This tells our Oak server that incoming requests will be coming in through port 8000. And all the listen function is doing here is it's wrapping the serve function in the standard Deno HTTP server, which we can see down here. It's passing in the port in exactly the same way. Don't worry, Oak is going to do a lot more for us than the standard HTTP server. The other method on the application class is the .use method, which registers middleware with Oak. And middleware is what Oak is all about. Pretty much everything we add is going to be middleware in some form. Middleware are just functions that are executed in order every time a request is sent to our server. And each Oak middleware function takes a context or CTX parameter. So we can see by calling app.use and passing in CTX inside of the middleware function. CTX, or context, is an object which contains the current state of the application. It has two main properties, request and response. But to get a more complete picture of what it looks like, let's check the Oak documentation. So in our oakserver.github.io page, we have a Deno doc for Oak. And listed under classes, we have our context object. So here we can see that context is a class that has multiple different properties: app, cookies, request, response, and state. The two that we'll be using 99% of the time are request and response, where request is an object which contains information about the current request that's coming into our server, and response is an object which contains information about the response that will be sent when the middleware finishes processing. This just means that all of our middleware functions have completed their execution. In our first middleware function, we're going to use the context.response object and set the body property, which will send whatever we set it to back as a response to the incoming HTTP request. So we could set the body to something like hello world, but that's boring. We're making an API for NASA after all. So let's use this fantastic ASCII art instead. And before we run our program, we're going to take advantage of our import.meta.main property that checks whether our module is currently being executed as a program. And we're going to pass in our app.listen there. And we have to remember to call await on our app.listen function, because this is going to be an asynchronous function. We'll now run our program by passing in only the allow net permission, because we'll be accepting incoming network requests and sending a response back. And now, after we execute our program and allow it to download Oak, looks like we got an error. Port needs to be capitalized. So once we execute this, we can browse to our site from the browser. And it's hosted at HTTP localhost on port 8000. There you go, our first Oak application. I'll see you in the next one. Welcome back. Before we really dive into more API code, there are two ideas that come back again and again in Oak. And those are middleware and the context object. Middleware are just special functions that run between or in the middle of the request coming into our API and the response coming out of our API. These functions always look like this. They always use app, which is our application object, and they are set or registered using the use function. And the use function takes a function, usually an asynchronous function, as its parameter. This function takes a context parameter and optionally a next parameter. The logic goes in the body of this function, where we work with the context to respond to our API request. And this can also be an anonymous function. So we could get rid of these keywords and just say async, context next, and use the arrow syntax. We'll be seeing app.use a lot in Oak. Now, we'll get to the next function in just a moment, but the context object here is key as well. This is an object that holds all of the relevant data coming in from the client in the request and all of the data about the response that our API will send back. These are two objects that are available inside of the context object. And the request is an instance of the request class, while the response is an object which is an instance of the response class. Now, some of the data that the request includes methods for are the URL that is being requested, secure, which returns whether the request was being made over HTTPS or not, whether it's encrypted, the method, which is usually one of get, put, post, and delete, and the body, which is the parsed body of a request coming into our API. So usually that's for post or put requests. Usually our get requests don't have a body. But this method here will return the parsed body, depending on the type of input that we're receiving, whether it's JSON or text. And finally, another noteworthy one is headers, which will return the list of headers that were sent in that request. We can see for the response that we also have headers, and we also have a body. But these are very different than the request, because on the response, we're setting the headers that we want to return back to the client in the response. And we're setting the body of our response. For example, what is the planet that is currently being fetched? The key difference here is that the methods on the response object usually contain both get and set methods. So I can do context.response.headers.set, and then I could get the header that I just set. Whereas on the request, the data is read-only, because the request that has been made by the client is already set in stone. So we could only do context.request.headers.get to see, for example, the content type of that request. Now, we'll see more of this in the coming videos, but for now, let's look at the status flag. So the status method allows us to set and get the HTTP status code of the response that we send back. So that could be 200 for a success, or a 500 for an internal server error. Again, we'll go over all of this in more detail in the coming videos. The important part here is getting acquainted with this context object and the various pieces of the request and response that we can manipulate in our Oak middleware. So we also have a content type on the response, and the redirect method, where we can redirect that response to another URL. Okay, so now that we've had a taste of what the context object contains, let's look at that next function for a second. And let's look at the flow of our middleware. You see, our middleware starts executing when a request comes into our API. It hits the first middleware, the one that was registered at the top, and we can see that this middleware has three pieces. It has the app.use, which registers the middleware, the context object, which we just learned about, and the next function, which controls the flow of our middleware. So when the next function is executed, the second middleware starts executing. And we're in a similar situation, where we can manipulate the context object again, and choose to call next, which will go down and execute the next middleware, which we might call the downstream middleware. And in this case, we can see that our third middleware here is an endpoint. So you can see that all three of these middleware have the app.use function and the context in common. The next parameter is optional. By not including next in your middleware, you're effectively saying that your middleware is now an endpoint. That is, it's the last piece of middleware in the chain. It usually sets the response body and returns the flow back to the middleware above it. So our second middleware continues executing until it returns, and our context trickles up from the bottom back to the top until all of our middleware has executed and we have our response ready to send back to the client. So we can see here that the next function is what is responsible for the order of execution of our middleware and making sure that we go all the way down. And then as our middleware finish executing, we go back up until all of our middleware have returned. Okay, I know that was all pretty theoretical, but don't worry. We're going to really apply everything we've talked about in the upcoming videos. I'll see you in the next one. Welcome back. In this video, we're going to really understand middleware. And by doing so, we'll unlock the full capabilities of Oak. Let's use the power of middleware to log the requests that are coming into our server. So now in our code, we'll put our logger middleware in front of our ASCII art middleware. And we're going to say app.use and pass in the context again. But now there's a new parameter that our middleware gets passed by Oak, and that's this next function. This is an asynchronous function that allows us to control exactly when the next piece of middleware is called. The key here is that this is an asynchronous function, so we need to make our middleware async now. And when we call next, we need to do await next. Now this here is telling Oak to continue executing the other middleware in the chain, and then after this next resolves, we can access everything that the downstream middleware has done, where downstream just means the middleware that comes afterwards. So in this case, our ASCII art middleware. For our logger, what we're going to want to do is console.log, and we want to log the request that came in. So let's check our Deno documentation for Oak. And as part of this request class, that's part of the context, we can see that we have a bunch of methods. Among others, we have the method, which is the HTTP method used by the request, which would be one of get, put, post, and delete. And we also have the URL. So the parsed URL for the request, which complies with browser standards. If we combine these two, we can get some pretty meaningful logs. What we're going to do is we're going to pass in context.request.method and add after it context.request.url. Let's run our program and test it out in Postman. Our server is running, and now we'll go into Postman, create a new collection. Let's call it NASA Deno. And inside of our collection, we'll create a request. It will be to get the ASCII art. We'll save this to our NASA Deno collection. And this is going to be a GET request to the very same URL that we hit before. It's going to be HTTP, localhost, and port 8000 with the root route. Let's save this and see what happens when we make a request. Hey, there you go! We got our ASCII art back in Postman. Let's check our code out again. It's interesting to know that we could pass in next to our ASCII art. After all, everything here is middleware, just like we talked about. So we could make this middleware take in the next function, and we'd have to make it async again, and then call await next at the very end. And let's see if it still works. Go back to Postman, make another request. Hey, there you go. It still works, but it doesn't really have an effect because our ASCII art is a certain type of middleware called an endpoint. That is, a middleware that doesn't call any downstream middleware. It just sets a body and returns. Even if we call the next function, there's no middleware after we've set the body here. Awesome. We're almost there. For our next middleware, remember how in Postman we got our status and also a response time? What if we wanted to include the response time in our log? How would we measure the performance of our server inside of Oak? Well, we want to measure the time it took to respond to a request. How would we do this? We would add a middleware below our logging middleware. And we'd do the same as before, async, context, and next. We'll want to measure the date and the time when the request started and the date and the time when the request completed and measure the difference. So we can do const start equals date.now. This is going to get the number of milliseconds since the start of the epoch. So that's since January 1st, 1970. And we're also going to measure an end or a time delta. And that's going to be date.now minus start. So what do we do in between here? Well, we use the power of this next function. You see, here we're calling the downstream middleware. So our mission control API text here, after we've started the timer. And then once that middleware completes, we measure the delta. Beauty. So how do we save the result of this? Well, we can use context.response.headers and set an HTTP header on our response based on the response time. So we'll pass in set, and we'll call our header x-response-time. It's common practice to set headers with this x- convention, as these are non-standard headers. And headers are usually metadata about the response, or data that the server wanted to send us, but not as part of the body. And we're going to pass in our delta here as part of a template string, and say this is the amount of milliseconds it took for our response to come back. Now in our upstream logging middleware, so the middleware code that executes after our response time middleware has returned, in that upstream middleware, we'd have access to this context.response.headers. And we could include this here by fetching it. So call time equals context.response.headers.get and our old x response dash time. Final step, let's add this to our response. We'll say time. Let's make sure this works and do some debugging in Postman. So we're going to rerun our program. And when we make a request, we can see that Postman is telling us the time it took was 12 milliseconds. Let's see how that compares to our logging middleware. Our logging middleware is telling us 0 milliseconds. There's a bit of disparity here because our middleware is only measuring the time it took for this body to be set, whereas Postman is measuring the entire round-trip time between our response and our request. The good news is we now have access to both pieces of data for some really fine-grained performance testing. And the final test, let's see if this data came back in our headers. All right, we can see X response time was set as an HTTP header in our response. We're starting to do some pretty fancy things in Oak. I'll see you in the next one. We've found ourselves in quite the position of responsibility. Here's the situation. As a follow-up to the Artemis project, which brings people back to the moon, NASA is looking to collaborate with us, Zero to Mastery, to create a new launch system for interstellar travel to other planets. Can you believe it? We'll be adding on to the SpaceX launch system that will allow us to target our launches to the Kepler exoplanets in other solar systems. Our front-end developers at NASA have handed us a website design in this folder, and they've completed some work that includes some static HTML, some CSS, some JavaScript, and a favicon. Let's take a look. Because this is just HTML, I can find this folder, and if I double-click it, we have our mission control user interface. So you can see we have the ability to schedule a new mission launch, and this takes a launch date, which is a calendar date. We have a mission name, a rocket type, of which there's currently only one, and a destination exoplanet. We also have the ability to list upcoming missions, which each have a number, a date, a mission name, a rocket, and a destination, as well as the ability to abort a mission. And we can also view all historical missions, which has a similar set of information, with the exception of this customers field. Okay, now that we have a slight idea of what we're trying to build, I wanted to take a moment to give a huge shout out to Advent of Code for their simple and great design. Turns out that the minimalist design is just what NASA likes. But in all seriousness, adventofcode.com is a site that for 1 month a year gives you daily programming puzzles for a variety of skill levels that can be solved in any programming language you choose. Don't worry, if you missed it, the puzzles are available year-round. It's a great site for coding challenges, and it's a great outlet for learning new languages and new runtimes. So give it a try with Deno and TypeScript. You'll definitely learn something. Okay, moving on. The engineers at NASA have told us at Zero to Mastery that the front-end code is ready to be integrated with the back-end. This is a common situation in web development. The front-end is often made ahead of the back-end, so we're getting some good real-life experience here. The truth is, the front-end usually needs to be modified after the implementation on the back-end is already underway. Because it's very difficult to predict the exact constraints or implementation choices that will be made on the back-end. We still need to actually implement the logic and the data to make this all work. Let's go over the JavaScript that the front-end engineers at NASA sent us so we can get a better idea of the work that we have ahead of us. So we can see straight from the top that we're going to be keeping track of launches. And then we have a bunch of heading information. This is some UI code with some white space padding to make sure that everything is aligned nicely. And then we have this initValues function, which sets a date. If we run this in our Deno REPL, we can see that this takes the ISO string in the shortened form with just the year, month, and date. And it takes this and sets the minimum date and the value of this calendar date picker here. And then we have a load launches function, which still needs to be completed, but we've been told that we need to load the launches and sort by flight number. Okay, so that's probably going to be populating this launches variable. And we have a load planets function as well, which seems to populate this planets selector with a bunch of HTML that takes this Kepler name from our planet. So we're going to need to fetch the planets from the API as well. We also have an abort launch, which we've been told deletes the launch and then reloads the launches, probably to make sure that the front end has the latest set of launches. And moving along, we have submit launch, which we can see submits the data above to the launch system and reloads launches again. So we're submitting, this is key, a target. This is a planet. So the target planet, the launch date, which is the date from that calendar picker, a mission, which is a name, a rocket, which is also a name, so these are going to be text fields, and then a flight number, which is calculated based on the amount of launches currently and the latest flight's flight number. So we increment that by 1 every time we submit a launch. And moving down, we have list upcoming. So this selects this upcoming list div and populates it with these launches, which we can see are being filtered based on this launch.upcoming property. So it makes sense that the upcoming list is only taking the launches that are upcoming. And then we have a bunch of text formatting code here. One thing of note here is that we're using this nullish coalescing operator on the target. So this acts like the double OR operator, except it only returns this second field here if the target is null or undefined. Whereas with the double OR operator, it would return this parameter here if target was null, undefined, or any falsy value. So 0 or false or anything like that. And we can see that for the launches, we're displaying the flight number, the launch date, the mission, and all the other information that we saw previously. And we have a similar function here for history, where it's filtering by the opposite condition. So only the launches that are not upcoming. So the launches that have already happened. Moving down, we have the navigate function. And we have the ability to navigate to these 3 pages: history, upcoming, and launch. When we navigate to one, we set the element corresponding to that page to be visible and set the other elements to be hidden, as well as making this launch success hidden as well. That's probably to reset the launch success status. And then we have some logic here. So for the upcoming page, when we navigate to it, we load the launches from the API, and then we list the upcoming launches. So we refresh that part of the data. And something similar for history. We load the launches and refresh the history data in the HTML. Okay, so these are where our APIs are being called when we navigate to these separate pages. And finally, we have the window on load method. So when this page is first loaded by the browser, we init those values with the calendar date, setting the minimum and the value as we saw up here. And then we load the launches and we load the planets, as we see here. So we make these API calls the first time we load the page as well, to make sure that we have all the data that we need. Looks like we have our work cut out for us. We're going to have to implement a few different endpoints here. There's going to be a launches loading endpoint, a loading planets endpoint. These are probably going to be GET requests. And there's going to be an abort launch function, which will most likely require a delete method. And finally, we have the submit launch endpoint, which is most likely going to be a post request on this launch data. Let's find out how we're going to do this in the next video. I'll see you then. Welcome back. Now that we've done our code reading, let's take the first step to making our mission control project. We're going to take the code that our imaginary NASA front-end engineers wrote and serve it as a web page from Deno. So how do we serve static files from Deno anyway? Well, we're going to start by renaming this folder to public. And that's going to represent the files that we're allowing our server to expose to the internet. And we're going to make some middleware to do this. So let's start by putting our app.use here. And we're going to make an async function that takes the context here. Notice that we're not passing in next. This is going to be another endpoint. The middleware ends here. We're the last one, the endpoint. And we're going to import this send function from Oak. Let's take a look at this function in the Oak documentation. So if we can see it right here, the send function. It fulfills a response with a file from the local file system. And it's asynchronous and requires the Deno read permission. Okay, so that means that we're going to have to await this function. And we're going to pass in some parameters. So we're going to start with the context. And the next parameter was the path name. So we're going to define a variable called, let's say, file path. And we're going to use the context.request.url, just the same as in our logging middleware. So we're going to do context.request.url. But this time, we're going to take this path name property, which takes just the last part of that URL, just the file name. And we're going to pass in our file path, as well as some options. Let's take a look again at what options the send function has. So we have this options parameter here, which is a send options interface. And we can see we have a whole bunch of optional properties here. We have this question mark. That's what the question mark means in TypeScript. So these are all optional. We have, for example, a hidden property that allows the transfer of hidden files, which defaults to false. That's a good thing. Usually files are hidden for a good reason. But we have this one required property, which is the root directory to restrict file access. We can see from the start that this send function is following some good security practices. We'll go more into that in just a second. So we're going to pass in our root, and this is going to be this public folder over here. So we need to pass in public, but we want to make this an absolute URL, an absolute path, because we want to be extra specific about which files we're serving. So we're going to pass in from this Deno global, we're going to use this cwd function for the current working directory. That's the directory that we're running our Deno run command from. Okay, and we're going to add public to that. But before we run our program, we're going to do one more thing. Remember this concept of whitelisting? This was explicitly allowing only certain entities access to a particular privilege. So in this case, to being served from our server. We want to make sure that Deno is only serving the files that we expect. We don't want to serve, for example, our source code by mistake, or a file with application secrets, like credentials to AWS. This is always good practice when a piece of code has the possibility to do something unexpected with serious consequences. Serving files and serving private files is definitely one of these cases. So we're going to go back to our code, and inside of our middleware, we'll define a file whitelist, which is going to be an array of the different files that we want to serve. So we're going to start with index.html. That's coming from this public folder here. And we're going to include all of these files. Great. Now that we have all our files, let's make sure we can run our program. And let's make sure we're using the right function here. So this time, we're going to pass in, same as before, the allow net permission, but also the allow read permission for our static files. Now, when we run this, we should have access to our NASA mission control frontend from Deno. So if we load our localhost port 8000 page and try to load index.html, we have it. Success. And we can browse through just like before. Let's take a look at our server to make sure that all of our files are being served. Perfect. We have index.html. That took 4 milliseconds. We have our styles, our script, and our favicon. We're starting to see our logger and our request timing middleware in action. Okay, so let's just make sure that our ASCII art can still be loaded as well. So that was when we make a GET request to the root. And hold on, we got a 404. We have a problem now. We can't serve both our fancy ASCII art and our files at the same time. They're both being served from the root, from the same URL. You see, they're both endpoints in our middleware. And because our file middleware came first, it's overriding this ASCII art middleware that we had. We're going to need to support multiple different routes. There's no way around it. And for that, we'll need a router. Let's learn all about it in the next video. Welcome back. Before we move on, we need to fix an error in our program. I've forgotten to do something. Did you catch it? That's right. I made this whitelist down here and I forgot to actually check it when we serve our static files. So what we should be doing is checking if the file whitelist includes the file path that we're being asked for, and only then send the files back to the browser. This way, we're only publicly serving files that we've approved in our whitelist. This is a great example of where something like pair programming might have saved the day. When pair programming, there would be two developers sitting at one machine, working on the same problem. We would each take turns writing code while the other one observes. You would have had my back, right? All right, I knew I could count on you. We just saved ourselves from a potential security incident. Disaster averted. I'll see you in the next one. Previously, we discovered that we can't serve both our ASCII art middleware and our static files at the same time. We're going to need something called a router to be able to do this. Now, a router is a common concept in both front-end and back-end code. Routers allow us to respond differently from different paths with different URLs. So just like on GitHub, when we navigate from the main page of our repository to the issues page, we get a different URL representing that page. On the back end, we could browse to the planets URL, for example, to get a list of all the planets from our API. Or say we wanted to get the information for a specific planet. We could query it by ID. And our router would point the browser to the correct endpoint in our API to send back the information for the planet at that ID. Routers are what allow us to do all of this. Now, let's think about this for a second. How do we do routers in Oak? Everything else was middleware, so that's right. Our Oak router is going to be middleware too. We'll start by creating a new file, and we'll call it api.ts. We're going to import our router from our Oak library, just like before, and we'll create a new router object by creating a new instance of our router class. Now, what does our router do? Well, it registers middleware that will run when certain HTTP methods and paths are requested. So it allows us to map a combination of an HTTP method, like GET, with a specific path, like planets. And when that path is matched, it will execute whatever middleware we've registered at that route. And for each HTTP method, like GET, our router has its own corresponding method. So one of our options here is to pass in the path that we want to match, and then the middleware that will execute when somebody requests that path. Okay, and since our ASCII is what we want to move to our router, and it always just responds with the same text, we can use this get method. And our first parameter is going to be the name of the path. So if you remember, we wanted the ASCII art middleware to show when we browse to the slash endpoint, the root. So we're going to do that here. And in our function, in our middleware, we're going to pass in context just like before, where we'll set our context.response.body to our ASCII art text. We're going to use an export using this default keyword here to export our router, because it's the only thing in our module. So now that we've used the default keyword in our mod.ts file, we can import our router by doing import, and we can name it whatever we like. So we could call it pizza, and then do from api.ts. And that would work as well, because there's only one thing that our api.ts exports. But for now, let's stick with API. And we're going to replace our old code with this api.routes middleware from the Oak router. As we can see in the documentation, this will return middleware that will do all of the route processing that the router has been configured to handle. So now when Oak gets to our routes middleware, it will know which endpoint should handle that request. And we're going to need to move this routes middleware to in front of our static file middleware. This is so that our API catches all the different routes that we want to support. And anything that doesn't match that, for example, index.html, will be sent to the static file middleware, which will look through our whitelist, and if there's a match, we'll serve our file. Let's see this in action. Okay, so let's make sure that we can get our index.html first. There we go. We're still getting our dashboard here. But can we do what we weren't able to do before and get the ASCII art at this root route? Yes, we can. We're now getting our files and our ASCII art from our API. Okay, but what happens if nothing matches? So what if someone tries to navigate to localhost / doesn't exist? Well, there's no route in our router, and the file doesn't exist in our whitelist. So our function here just returns without setting a body. And Oak will actually take care of sending back a 404 not found error. So if we navigate to doesn't exist, check it out. We got our 404. None of our middleware set a body for this request, so Oak knew what to do and told the browser that this endpoint doesn't exist. It's not often that I'm this happy to see a 404 page. Alright, I'll see you in the next one. In the last video, we added a router to our Oak program and learned how to use the routes middleware. You may have noticed in the documentation that it was mentioned typical usage would be something like this, and the routes middleware was followed by this allowed methods middleware that our router also provides. So what does allow methods do? To understand that, let's look at our HTTP methods again. So far, we've been using the get method pretty exclusively, to fetch data or text from our APIs. Let's take a look at the post method now. This corresponds to the create option in our CRUD model. We use HTTP post methods to create data in our API, in our database, in memory. And the most accurate HTTP response to a post request is a 201 created response. In our HTTP response codes, we have these entire ranges of possible response codes. And for example, for the successful responses, the most common is a 200 OK. This means that the request has succeeded. But for post requests, where we're creating new data, we can do better than that. We can tell the client, the person making the request, more specifically that if the request succeeded, the resource or object that they wanted to create in the API was actually created. This is a more specific HTTP response that a post request can give us. That differentiates it from a GET request. Okay, so what does this have to do with Oak or our API? Let's look at what happens when we try to make different kinds of requests against our API. If we make the GET request against our route, we get our ASCII art back with a 200 status. And we already saw that if we hit, for example, doesn't exist, that we get a 404 not found. But what happens if we request a post against our root route here? What do you think will happen? Well, we get a 404 not found as well. And that's true. We technically don't have an endpoint that matches a post to our root route in our API, right? Our API currently only has this GET. But a 404 response isn't very specific, right? Remember how our post request can respond with a 201 to be specific that a resource was created. Well, if we look back at Oak documentation and scroll up to our allowed methods, middleware, we can see that it handles requests for HTTP methods registered with the router. It's not very specific, but we can also see that it talks about not allowed logic if none of the routes handle a method, and not implemented logic if a method is supported by some routes, but not the particular matched router. And also that it will automatically handle the options method. What does all of this mean? What's not allowed logic and the options method? Let's take a look at what happens when we add this allowed methods to our API. So right below our routes, we're going to say app.use api.allowed methods. And we're going to restart our server. And let's see what happens when we make a post request against our API now. We get a 405 method not allowed. A request was made of a resource using a method not supported by that resource. That's exactly true. It's much more specific than saying that it wasn't found, 404. So that answers the not allowed part here. But what about this options method? What's that? Well, back in Postman, we can see that there's actually a whole lot of different HTTP methods that we can make. And most of these we'll never make in our careers as software developers. But there's one of particular interest here, which is the options method. And now that we've added the allowed methods middleware, we can actually make an options request against our API. we can see that we got a 200, but there's no response. There's no body. Well, it's true there's no body, but we got some interesting information back in the header. What an options request gives us is the allowed methods on that particular route. So we're being told that we can make a GET request, which we've seen, and we can also make this head request, which is another HTTP method that returns the same thing as GET, just without the body. Why would you ever want to do that? Well, when we do a GET request, we're essentially downloading a file, right? Well, head can be used to get information about that large file without downloading it, to save on bandwidth, for example. Okay, I hear you asking, that's interesting and all, but what can I use this for? And why does options even exist? Well, think of it as documentation for our endpoints. It helps make our APIs discoverable for machines, for things like web browsers, web crawlers, or anything trying to find out what functionality our API really supports. We want our API to be a good team player that makes it easy for those who are using our API to know what routes we support and to get specific status codes back from the requests that are made. And the allowed methods function from the router allows us to do that automatically so that we as developers don't have to think about it. Very convenient. Allowed methods makes us a good team player. I'll see you in the next one. Welcome back. I know we've been talking a lot about middleware and routes. Weren't we supposed to be building a NASA mission control API? We had to get the basics in place so that we had the building blocks that we can use for any API in Deno. But I agree, it's time. Let's start with the planets project from earlier in the course. We're going to integrate this into our API and use it to build our mission control dashboard. So I'm going to start by copying over the files from this project. Okay, and now that we have the files that we need, we're going to start by structuring our old planets code to fit in with a larger API project. So this planets CSV, where all our planets data came from, this is data that's not likely to change. Unfortunately, the Kepler telescope, which gathered all of our planets data here, is no longer operational. So it's not going to be sending us any more planets. The good news is that means we can just put this in a data folder and use that as the source of truth for our planets going forward. Now our CSV takes the place of a database or an external data source of some sort. And I'm going to create a models folder where I'm going to put the planets code from before. This represents our data model. Our data model might get its data from a database or from another API or somewhere on the internet, but it provides a way of accessing our raw data and then an interface for accessing that data from our API. Okay, so just to recap here, what our code does is it reads in this CSV file with thousands and thousands of different Kepler planets, and it parses that file into an array of planets, which we then filter for specific criteria that match planets which are likely to be habitable, which are similar to Earth in some way. And then we pick only certain properties from those planets. Now I'm going to clean up some of our code here and move our list of planets to the top of the file. where I'm going to say planets is an array of planets. Just so we're clear that this is where all of our planets data is stored. And I'm going to assign it, same as before. So this array is going to be our basic planets database, living in Deno's memory. Now that we have our planets set up, after we load planet data, we're going to need a way of accessing this database. This is going to represent our data access layer. So the way in which our API accesses the data which we get back from our CSV database. And this is going to be simple. It's just going to be a function which we'll call getAllPlanets. And it's just going to return our planets. Now, for this to be accessible outside of our planets module, we need to export this function. Okay, time to make our get route. In our api.ts, we're going to create a router.get on our /planets path, where we're going to set the context response body to, well, something we import from our planets model. So we're going to do import star as planets from our models planets model.ts. Notice how even though this is a relative import, a relative URL, it's still following Deno's URL convention. It still ends in a .ts file. It still ends in a .ts extension. So now that we have access to our planets, we can just set the response body to planets.getAllPlanets, which we just defined. Okay, and we're set up. Just one more step we have to take before we run this. We have to make sure all our paths are correct. So our CSV file is now in our data folder. And we can run our program. We're seeing that the data got loaded correctly. Now let's make sure that our route is working. So we're going to query the planets collection. And we're going to save this as a new request. So we're going to say get planets. We'll save that to the collection and make our request. Hey, there you go. We're getting our list of habitable planets through our API. Our backend is starting to do something useful. I wanted to point something out here in how the planets module is being used. Deno is using ES6 or ECMAScript modules. These modules are cached, so the first time our planets module is imported in our api.ts file, it will create this object of planets, this array of planets, and on subsequent loads of our module, on subsequent imports, it will always use the same object. This is known as the singleton design pattern. What singleton means is that no matter how many times you import our planets module from our Deno program, if it's being reused in other models, for example, or in other API files, there will only ever be one list of planets. We can see this, for example, by moving our planets import to our main mod file. So we can import our planets. We don't have to use them. We'll get this warning, but we'll see that our planet finding code is only going to run once. Even though we imported the module in two different places, the code from the planets module here was only ever run once. This is a useful concept. Deno is minimizing the amount of work it needs to do. If we wanted to have a piece of code execute more than once, we would have to put it inside of a function and call that function multiple times. All right, and while we're here, I've just thought of something. We have this planets interface. This was to tell TypeScript that a planet is an object which is indexed by strings. So the keys of our object are strings and are indexed using this square bracket syntax. And the values of our planet object are also strings. This is such a common pattern in TypeScript because we're always working with objects that have keys of a certain type and values of a certain type, that several years ago in TypeScript version 2.1, Microsoft, who's behind TypeScript, added a shorthand for doing exactly this. We can now use a record type by writing record and saying that we have string keys mapped to string values. And this is the same if we assign it to a type and call it planet. This is the same as doing this interface here. But it's a fair bit more readable, don't you think? So let's leave our code in a slightly better spot than we found it. There we go. Much better. I'll see you in the next one. Welcome back. Now that we have our planets endpoint ready, let's add the planets data to the front end. So inside of our front end code, we can see that we're getting a few warnings from TypeScript, complaining about implicit typing and saying that the document object can't be found. If we don't want our front-end JavaScript to be parsed by Deno, we can add this TS no check line at the top of our file to prevent Deno from running TypeScript checks on our JavaScript. Look at that, no more warnings. Okay, so we're going to scroll down to where we're calling our load planets endpoint, and we're going to uncomment some of this code here. This is the code that takes the data that we've fetched and populates this series of options fields with the name of our Kepler planets. So it looks like we're going to have to do a fetch on our planets endpoint, and this is going to default to a GET, as well as making the request to the same server that's currently hosting the front end. So because Deno is both hosting our API and serving our files statically, we can just pass in the path to our endpoint directly without giving a host or a port or any other identifying information for our server, like an IP address. Okay, so we're going to use a promise chain with the promise that's returned by the fetch function, this beautiful fetch function that's exactly the same on the front end and on the back end, and we'll take that response, calling it planets response, and just return in this first step planets response.json. And if we remember our fetch example, this is going to take the body of the response and parse it as JSON, returning us back the parsed JSON object. So our job now is easy. We can just pass in the result of our JSON call as a series of planets and render our HTML using this vanilla JavaScript here. So this is going to take the Kepler name from our planets model that we selected here using the pick function, and it's going to populate our planets selector with that data. So final step, we're just going to return the result of this fetch, and there we have it. Let's see if we're getting our list of planets in the front end. Our selector is getting our list of planets. We now have 8 planets that are candidates for our mission control launches. We're one giant step closer to being ready for launch. Okay, but something else has happened here. Just like we expected, the front-end engineers couldn't predict the future. And some of the requirements for the planets that we're targeting have changed since the initial site design. No worries, software is alive and changes all the time, so we're just going to update the front-end code to accurately represent our new criteria. So our HTML is saying that our solar mass needs to be within 10% of our sun's mass. But that criteria has changed. If we go back to our filter function here, the mass needs to be between 78% of our sun's and 104%. So we're going to update that field. We'll do the same for the solar radius. That needs to be within 1% of our sun's radius. And finally, we'll add this last criteria that didn't exist before, which is going to be the planetary radius between half that of Earth and 1.5 times that of Earth. Let's make sure our UI is updated correctly. Success! I'll see you in the next one. Let's talk about testing. Testing allows us to fix problems with our code. It helps us to catch problems before they happen. And it gives us more confidence that the code we write is actually going to work the way that we expect. It's something every developer does, whether you're following this test-driven development model, where you write the tests before the code and use them as a specification, as a target for what your code should accomplish, or you can write the tests after your feature, after writing the code, as a way of validating what you've already written. Developers tend to have a lot of differing opinions on this topic. I personally don't think there's a wrong way to go with testing, as long as you do it. What I do myself is, if I notice I'm writing a piece of code with several different branches or possible paths through the code, for example, like this planets filter here, where a planet can be filtered based on whether it's confirmed or not, and based on any of these criteria, where a value can be less than or greater than the required amount. In these cases, writing the tests in parallel with the code helps me maintain context on what I'm trying to achieve, and it also forces me to consider and handle all of the different possibilities in my code as I'm writing it. This leads to better code. Whether you like it or not, if you ask any programmer what they're doing at any point in time, there's a good chance they'll say testing. So let's look at how Deno makes testing easy for us and write some tests. I've created this planets.test.ts file here for some tests for our planets model. Before we get into writing any tests, let's look at some things that Deno includes out of the box. The first one is it includes this test runner in the CLI. If you've worked with Node, you might be familiar with Mocha or Jest. These major third-party testing frameworks. The choice between these testing frameworks is often subject to a lot of discussion and disagreement between developers. And it can cause a bit of decision fatigue, where rather than focusing your energy on solving the problem at hand, you're spending your energy deciding which framework to use. Deno decreases the cognitive load on you by giving you tools like the test runner built into the code of Deno in the CLI, the command line interface that allows us to do Deno run and Deno install. When we run Deno with the test command, this takes your test files, for example, those that end in .test.ts, and it runs them and gives you a report on which tests in those files succeeded and which ones failed. Right now, because we don't have any tests, there's 0 for both. Deno also includes an assertion library as part of its standard library. We can browse to the documentation and see that Deno provides a series of assertion statements as part of this library, including some of your favorites like assert equals and assert strict equals, which uses strict equality. Even things like assert throws, where you can check that a function is throwing an error, and even which error specifically it is throwing. But also some less common ones, like assert throws async, which makes sure that the function is async, and that it returns a promise that rejects. We'll see this in action in just a second. But the last thing that Deno includes is built-in test fixtures, or test cases, using this deno.test function. This allows us to register some tests and do any setup for the test using a function built into the Deno namespace. Let's go over some examples of Deno's testing abilities. I'll see you in the next video. Let's look at all the different things that Deno's test runner allows us to do. Starting from this test function, we can see that our function takes a deno.test definition. This is a type that's going to be defined in the Deno namespace, in the Deno runtime. So if we check out the documentation, we can see that the test definition interface has a few different properties, the two mandatory ones being a function and a name. So we can define a test by passing in an object, naming our test, so for example, example test, and then defining the test function using this named function. In this function, we can do something like console.log and say hello from our tests. Now, as we saw previously, the most basic way to run our tests is to write Deno test. Here we see that our test runs. The test runner is taking all of the files in our project that end in test.ts, or potentially test.js, or JSX, or TSX. And it runs the tests defined with our deno.test function that are contained in those files. We can also pass in specific files to test if we want to only run some of the tests in our file. So we could say Deno test models/planets.test.ts. And we can see that our message is being output from our test, and our test defaults to passed because we didn't have any assertions that failed. But our test right now isn't exactly useful. We're not actually checking for any functionality. So to do that, we'll need to import from our assertion library. So say we want to check for the equality of two strings. We would import our assert equals function from Deno testing library and this assertion model here. Now inside of our test, we can say assert equals and pass in, say, two values or strings. Deno is equal to Deno. And if we wanted to check for inequality, we could say import assert not equals. And we could pass in a different value, So for example, to object, we could say runtime Deno is not equal to runtime node. And that should be true. So if we run our tests, we can now see that our assertions are being validated. If we changed Deno to node and reran our tests, we'd get a failure. And Deno would tell us exactly why our test failed. Now, if this seems a little bit verbose to you, the good news is that Deno has a shorthand syntax for writing tests using common parameters. So instead of passing in this object into our test function, we can pass in a string with our description. So say example, short example test. And as the second parameter to our function, pass in our test. So we're going to use an anonymous function and make the exact same assertions as before. And let's make sure that our tests are passing. So make sure that we're setting the equality here correctly. Oop, not for that one. That one's supposed to be not equal. The strings here are supposed to be equal. So now if we run our tests, we should see 2 tests that are passing. Now, why would we ever want to use this long form syntax if we have this shorthand available? Well, as we saw previously, there are a few additional parameters we can pass in to this function. One of these is ignore. So this provides a set of conditions that we can pass into our function, and only when those conditions are matched or true. So in other words, if the ignore flag is set to true, our test is not run. And we can see this in our output, that this test is being ignored. When might this be useful? Well, we can do things like Deno ignore, checking the build operating system, using this built-in build.os to run certain tests only on certain environments. So in this case, I could run this test on the Darwin platform, which is the shared core between macOS and iOS. Or I could change this to Windows or Linux. And because I'm running on macOS right now, the test will execute because we're not ignoring our test. If I set this to Darwin again, I'll only get the one test. This might be useful when, for example, checking for the existence of a file, which might exist on one operating system, but live in a completely different location on another operating system. Okay, so what do these 2 other properties here mean? We see that sanitize ops checks that the number of async completed operations after a test is the same as the number of dispatched ops. And sanitize resources ensures that the test case does not leak resources. If we recall back to our deno.metrics function, remember how we could do deno.metrics? And this would give us a series of properties, 2 of which were ops dispatched async and ops completed async. These represent the amount of started asynchronous operations in our program up to that point, and the amount of asynchronous operations that completed up to that point. So if we did, for example, a set timeout, which is an asynchronous function, and wanted to do a console.log after 10 seconds, this would start an asynchronous operation, but by the time we call deno.metrics, we've dispatched 5 asynchronous operations, but only 4 have completed. What this would mean in our test, if we did, for example, deno.test, and in our function, we said set timeout, console.log, and wanted it to resolve after 10 seconds, when this function returns, not everything that we set out to do in our test would have completed. This is usually the sign of an error or an operations leak. So when we run our tests and do Deno test, Deno knows automatically that there was a problem with our test. It fails it, telling us that there was an error in our ops leak test. And it tells us specifically that there were more completed actions than dispatched actions after our test case succeeded. And it tells us specifically this test case is leaking async ops. And make sure to await all promises returned from Deno APIs before finishing the test case. I think that's pretty cool. The other parameter that we could pass in was the sanitize resources parameter. So now if we pass in our extra parameter and say sanitize ops false, in the odd case that you're doing this intentionally and don't need all of the operations in your test to complete, when you pass in this flag, Deno will now ignore that check. So our test passes. The other flag we had was sanitize resources. And we can see that this checks that the resource table after the test has exactly the same contents as before the test. So just like before we had the Deno.metrics table, we also have this Deno.resources table, which shows us a representation of all of the open resources, which includes things like files and output that are being used in our program. So Deno checks this too. We can do something very similar, let's say a resource leak example, and we're not going to pass in any sanitize ops. But say we do await Deno.open and try to open our planet's TypeScript file. So in models. So notice that now we have an async function. So we need to make our test async. But also that we're not closing this file. So there's a resource leak here. When we run our tests, Deno will catch this resource leak and fail our test. So now we can see that our resource leak test failed. And, actually right now it's failing because the permissions to open this file are needed on the test command as well. So I'm going to need to rerun it with the allow read flag. But now we're going to get another failure, which Deno is telling us is because the test case is leaking resources. And we can see here that before we had these 3 resources here, and now we have a 4th for this file that wasn't closed. Deno even gives us a suggestion to make sure that we close all our resource handles. We can see here how our knowledge of Deno internals is helping us understand and catch issues in our test cases. If we were doing this intentionally for whatever reason, we could say sanitize resources false, and our tests would succeed. Now that we have a good understanding of the different capabilities that Deno's testing framework includes, let's take a look at a couple of different ways we can run our tests. So if we pass in the help flag to our Deno test command, we can pass in all the same permissions as in the run command. And we can see that by default, it checks against all files that have test and dot in the file name with any of the extensions seen here. And we can also scroll through some of the test-specific parameters here. So we see that while it's still pretty bare bones and doesn't have things like test coverage reports or a built-in watch mode, like some of the more fully featured node frameworks, there are still some features that you might be familiar with from frameworks like Mocha. For example, we have fail fast, which will stop our tests on the first error. In case you have hundreds of different tests and want to save some time and only care whether all of the tests are passing or not. We also have this filter parameter, which allows us to filter the tests that we're running. So looking at the different names of our tests, we have short example test. Let's call this long example test. And then we have our 2 leaks. So we could choose to run, for example, our test command with the filter option, passing in short. And that will match the name of the test and only run the test that includes short in its name. Or if we were only interested in leaks, we could run the filter with leaks. With leak. And we would run the 2 tests that check for the different types of leaks in our program. Alright, that was a pretty long video. In the next one, we'll put this to use to write some tests and improve our code a little bit more. Let's put this into practice. I'll see you in the next one. Welcome back. When dealing with mission control software like space flights, where one error can mean billions of dollars wasted, testing is almost the most important thing we can do. We've added our planet's code to our project, but our code isn't exactly easy to test. You see, we're doing File IO. We're opening a file. We're parsing that file. We're doing our logic and mapping over that logic. The code with the most testability, with the most ability for something to go wrong, is this filtering function. But this functionality here depends on files being around. It depends on this parse being completed. So what if we wanted to test our habitable planet finding code here in isolation as a unit test? Even though we think there's nothing wrong with our code here, we can improve upon it and make it more testable at the same time. How easy your code is to unit test is often a good measure of how modular and well-written that code is. So let's do exactly that. Let's make our logic here testable in isolation. What we really want to test is our function, which filters habitable planets. And in general, we want our functions to be verbs. So we're going to say our function is filter habitable planets. And this is going to take in a list of planets and return a list of only those planets that match our criteria. So we want it to do exactly what we're doing here, just on this planets parameter. And we want it to return the result of that. Now we see TypeScript telling us that planets can be any, so we're going to be specific and say that planets here is going to be an array of planets. Now, when we use this function, we're going to replace this logic and call it on our result, which, if you remember, was the result of our parsed CSV file, but still use our type assertion to make sure that our function knows that we're passing in an array of planets and leverage our typing. Okay, so now that we've refactored our code, let's make sure that we can still run it. So let's run the model directly and pass in planets.ts, and we need the allow read flag. So we now know that our code is still working, or at least we know as well as we did before. We're going to be looking to get some more confidence about this code here that has our filtering logic. So to make this function available in our tests, where here I'm using basically the short example test as a starting point, we're going to want to be able to import our function from this planets.ts file. But for that to work, we're going to need to export our function. So now that we can import our function from our test file, we can start building test cases. And we're going to start by creating some test data. So because the different options in our function, the things that will determine the outcome, are different types of planets, we're going to create some planets for our test function. So let's start by a success case. So we're going to say habitable planet. And we're going to pass in all of the different properties that cause our function to succeed. So what planet has all of the criteria that we need from a habitable planet? Well, Earth. So Earth would be a confirmed planet. Earth has a planetary radius of 1 times the size of Earth. And our Sun exactly matches 1 solar radius and 1 solar mass. So this is what we want our function to return, but we also need to check some cases that don't get through the filter. So in this case, it's going to be us as developers looking through all of the edge cases in this function and trying to test those edge cases. Now, we're not going to be 100% thorough in this example because there's quite a few cases here, but we want to at least check the edges of these ranges. So for example, if a planet has a radius that's 1.5 times Earth's, it's going to get ignored by this function. So it's going to be better to test a value of 1.5 in this range than it would be to test a value of 10, for example, because we're testing exactly the bound of our function. All right, let's do that. So let's create a planet that is not confirmed. And here we're going to say that it was, for example, a false positive. Now, because our function uses short circuit operators, so these double and signs, which means that if this check fails, then these checks aren't even executed, we don't even need to include these other properties for this check. Let's create some more planets. Maybe one that's confirmed, but has a planetary radius that's of 1.5, like we talked about. So we're going to call this too large planetary radius. And then let's have one where the solar radius is too large. So too large solar radius. And the bound for that one was 1.01. And notice how we're isolating the test case. So our planetary radius now succeeds, but it's only the solar radius that we're testing for this planet. And as a last check here in our little test, let's do a planet that has a too large solar mass. And the bound for our solar mass was 1.04. Not our radius, but our solar mass. And we would do the same for our lower bounds, so make sure that we check all of these left-hand values. But for now, let's see what our test case would look like. So we want to make sure that we're filter only habitable planets. And we're going to use this assert equals, which does a deep equality check, and pass in a list of planets as the first parameter, and a list of planets as the second parameter. In the first parameter, we'll put all our different test cases, so habitable planet, and go through all of them. And now that we've passed in all of our planets with all of the different cases, we want to make sure that the only one that's returned, that's filtered, is our one habitable planet. And of course, what we want to do here is we want to not pass in the list of planets directly, but we want to call our function. So we're going to say const filtered equals the result of our function, passing in the list of planets. And then we're going to assert that our planets are filtered correctly. And let's run our tests. So we're going to do Deno test and pass in our allow read permission for our CSV file. Beautiful, our tests are passing. We now have that extra confidence in our code that it's behaving the way we intended. And we can continue developing our API with our assumptions about planets validated and confirmed. Sounds good to me. Now, we could have passed in our sanitize ops and our sanitize resource parameters and used the long form definition of our test case here. But we want to make sure that our files are being closed and our asynchronous operations are terminating. The short form syntax handles the vast majority of test cases that we want to create. Deno makes doing the right thing easy. Welcome back. If we remember our SpaceX example, we used the standard Deno logging module to add some more organization around how we use our logs. We could log with different severities from debug to critical at the highest severity. And we could set up log handlers that logged to the console or to a file. Now that our API is starting to become a bit of a larger program and we're logging things in a few different spots, we're going to slowly find that we have a few different categories of logs. Let's see how we can add some useful logging capabilities to our program. We'll start by importing the logging module, and we'll set up our logger here, right before registering all of our middleware. We're doing our setup exactly like we did in the SpaceX example, by setting up a single default logger, which logs everything at the info level and above. So info, warning, error, and critical, all to the console. Now with our logger in place, we can do a search and replace on console.log and replace it with console.info by default. So that includes a log here in our mod.ts file where we log our request. And we have our log in the planets file, which tells us the amount of habitable planets found. So let's do our replace all. And while we're at it, let's add a log here just before we start our HTTP server and say starting server on port and pass in our port. Just so we know at what point we've finished all of our loading operations, like parsing our CSV file for planets, and we're starting this call here to listen for API requests. Great. Now we have the ability to log to a file or with more severity by using, for example, the error or critical levels in our logger. We'll put this to use real soon. I'll see you in the next one. Welcome back. Let me ask you a question. What happens in our API if an error is thrown? In some cases, we can catch the error right away by wrapping it in a try-catch statement. So for example, if we're trying to wrap our deno.open, we can put try and then catch and do something here if our deno.open statement throws an error. But why would deno.open throw an error? Is it because the file doesn't exist? Or is it because we didn't pass in the correct permissions to read files? Sometimes the error is completely unexpected, or we just don't have a good way of recovering from it. If we can't access the file here, well, we can't really parse any of our planet's data, and our endpoints can't do anything useful. One thing we can do to help deal with these uncaught errors is to add some error handling middleware. Now, we'll want to do this right at the top of our middleware chain so that regardless of what happens afterwards, if an error is thrown, it bubbles all the way up to our error handling middleware. So we're going to use our standard async middleware function here, passing in next. And we're going to make use of our next function here. We're going to handle errors by seeing if this next call throws an error. So if any of the downstream middleware throw errors. And we're going to do that by wrapping this in a try and catching the errors that are returned from it. And we're going to do three things when handling our error. We're going to make use of our new logger and pass in the error into this log.error function to make sure that our errors are being treated at a higher severity than info. Now, if our log level in our log setup is set higher, for example, if we had a file handler here that only logged errors or critical warnings, the error we catch here would be logged. Next, we're going to set the response body and make sure that the person making the request against our API knows that there has been an internal server error. Something that wasn't quite handled on the server side that caused the request to fail. And we don't want to be too chatty about what went wrong in case this error includes some sensitive information that might be useful for hackers or malicious users to take advantage of these errors. And the last thing we're going to do is throw our error exactly the same as it came in. Our middleware here is not the final handler of errors thrown in our code. The Oak application will catch any uncaught errors that are thrown from our middleware. The application extends this event target interface that we have in our browsers too, that allows us to listen for events. And one of the events that we can listen for is the error event, which Oak triggers when it catches any errors that were thrown from our middleware. So we can listen for these errors by adding an app.addEventListener and listening to this error event. This will give us back the event as a parameter, and here we can do our final handling. This is the final resting place of any uncaught errors in our Oak application, and it's where we want to do our logging. So actually this log.error here will be moved to our event listener, and we're going to log the event, specifically the error field. Now, how can we see our event handlers in action? Say we were to go into the planets route. We could throw a new error before we set the response body. So say throw new error, and let's just call it sample error. And what happens now? We can go into Postman and make a request to our planet's endpoint. We're getting our internal server error with a 500 status code. So our error has crawled all the way up from our endpoint up through our various middleware, starting from the routes, up through our different middleware, into our error handling middleware, where we set a response body to what we just saw, and Oak returned a 500 status code by default, which we can see on the Mozilla developer documentation corresponds to server errors, as opposed to client errors, which usually have something to do with the way the request was made, the way the inputs were passed in from the client. Oak, however, provides a different way of throwing errors. We can use this convenient context.throw function and pass in an HTTP status to return. So we could say 501, which we can scroll down and see corresponds to not implemented. And we can pass in a second parameter here with a custom message, like, sorry, planets aren't available. Now this one's tricky. What do you think we'll see in Postman? If we rerun our program and go into Postman, we can make a request, and we get our 501 not implemented, but we don't get the message we passed in. We just get not implemented. This is because Oak isn't showing the specifics of the error that we passed in for 500 series responses. These are errors that are internal to the server and often contain information that we don't want to pass back to the client. But you can see here that we got the details in our log. Our logger here included our custom message as part of this error object. And if we were to change our API to return a 400 series error, so corresponding to client errors, and we go back into Postman, we now get our 400 error with our message. We now have the ability to tell the clients consuming our API specifically what went wrong in unforeseen situations. And we have the ability to log the specifics as well. I'll see you in the next one. Welcome back. We're here. We're about to implement launch functionality into our API. Let's get started. The functionality we want to implement is to be able to set up a launch date, a mission name, a rocket type, and a destination exoplanet, and use this data to create a mission. When we save a mission, we want to be able to view it in the upcoming missions list and display a series of data from those launches. And we also want to be able to list the historical launches, including SpaceX launches starting from the year 2006. So how are we going to do this? We're going to start from our SpaceX example earlier in the course. To recap quickly, we stored a map of launches that stored flight number, mission, rocket, and customer information that we gathered from the SpaceX Data API. We checked that the response from the API was okay, and then parsed the response for JSON, then going over all of the launches in the result and selecting the data that we wanted to save. Finally, putting it into our launches map. Okay, so the first thing I noticed is that there's a bit more data in our front end that we haven't captured in our code yet. So we have this launch date that we need to save. And then we need to have a way of distinguishing between upcoming and historical launches, as well as storing the target, the destination exoplanet. And in fact, if we go to the front-end code, we can see that when we're listing historical launches, we're also listing the success of the launch. And depending on that flag, we're displaying this rectangle with a different styling. So probably the failure is going to be red and the success is going to be green. So we have 4 pieces of data to add to our interface. So we're going to say that the launch date is going to be a number. We're going to use the Unix representation of time, the amount of milliseconds since January 1st, 1970. And upcoming is going to be our Boolean flag, which differentiates between the launches that are in the upcoming section and in the historical section. And then we're going to have our success parameter, which is going to be a Boolean. But we're going to make it optional because upcoming launches don't necessarily have a success, right? We don't know if an upcoming launch has succeeded or not. And we're going to have a target, which will also be optional because our historical SpaceX launches weren't interplanetary. They didn't have Kepler exoplanets to target. They were mostly targeting things like the International Space Station. So our target is going to be a string representing our exoplanet. And now for these new fields, we need to add them to the flight data. So we're going to say that the launch date maps to this launch date Unix field in our API response from the SpaceX API. So we're going to map it to this field. Next, we're going to take upcoming and map that to, let's see here in our response, the upcoming field. And last but not least, the success. So we know that historical SpaceX launches will have some information about whether the launch succeeded or not. There we have it, launch success. And we're not adding that target field that represents the destination exoplanet because the data that we're fetching from SpaceX won't have included that. That's going to be new data that we're adding as NASA for our interstellar flights. Okay, now we want to make sure that we're downloading our launch data when our module is imported as a module and it's not the main file. It's not being run as a program. So we're going to get rid of this if statement here and clean this up a little bit. And now let's get started implementing one of our endpoints. So we can start maybe with the historical data. Let's get a list of all of the data that we fetched from SpaceX and display it in our table here. So we're going to define a function here and call it getAll. This is going to be our data access function for getting all of the launch data. If our map here is our in-memory database, our getAll function here is essentially querying that database and formatting the results in a way that our API can use. So since we like JSON APIs, because we're working with JavaScript and TypeScript, we know that we need to represent our map over here as JSON. So let's have getAll return a list of launches. So a list of all of the values in our map. And we can do that by calling launches.values to get the list of values, the list of flight data, and we're going to call array.from on that list of values. So we go from this iterator result that our values function returns to an array, which we can then return from our function. Now let's export our function so that from our API.js, we can now import star as launches from our launches model, launches.ts. And now, just like we did for planets, we're going to create a get route using the /launches path and call the getAll function on our launches model. All right, let's run our API and see if we can make a request to the launches endpoint from Postman. So in our NASA Deno collection, we're going to add a request and call it get launches. And we'll use the /launches path under localhost. Let's save that and run it. We have our launch data, and we're getting back the date, the upcoming, and the success fields for all of the launches that SpaceX has had. Very cool. Now, we're not necessarily going to use it, but as an exercise, let's try to create a path to get a specific launch. So we can use our get here as a template, but we're going to need to pass in an ID. And we can do this by passing in this ID parameter and making this route parameterized. Oak knows that when I pass in this colon syntax ID, the thing coming after the slash in our path is going to be a parameter. And I can access this parameter by going if context.params and then selecting the name of the parameter. So in this case, ID. So I'm checking if this ID was indeed passed. I want to select a launch by that ID. So I'm going to get one launch and pass in context.params.id. And Oak will pass in all parameters as strings by default, so we need to make sure that we turn this into a number. Because in our launches collection, we defined our flight number as a number. And flight number makes a natural ID for our launch. So we're going to be querying on this property here. So let's see if we can implement this data access function for getting one launch. So we're going to do the same thing, export function get one. And this time it's going to take in an ID, which is a number. Remember how we converted it from a string to a number using the constructor syntax. And here we're going to return launches.get and pass in that ID. So we're querying our map, which has the number, the flight number, as the key. But we only want to get this if that ID exists. We want to make our function safe in case somebody's querying for ID 9 million and SpaceX hasn't had 9 million flights. So we're going to check if launches has this ID. We're checking if a launch with that ID exists in our map. And if not, then, well, we return nothing. So we can be explicit and say return null. And now in our route, we should be a little bit more careful with our parameters here. So what happens if the ID parameter can't be accessed because there are no params on our context? So we're going to use this optional chaining operator on our params field here, which will return undefined from this expression here if the params field doesn't exist, instead of throwing an error, because we're trying to access this ID property on a null or undefined value. This is essentially shorthand syntax for doing if context.params and context.params.id, which is another way of preventing this from throwing an error if the params doesn't exist, because it will return if this is false and never try to access the ID here. Okay, and let's be extra safe here and assign this to a variable. So say launches list. And we'll say only if launches list is truthy, so it's not that null value that we defined here, do we want to set the body to the launches list. And otherwise, we can use our context.throw function to return a 400 error, which is a client error, saying launch with that ID doesn't exist. All right, let's see this in action. So we're going to rerun our program. And in Postman, let's create a duplicate of our getLaunches request, and we'll rename it to getLaunchById. And for this one, let's query for, let's say, launch 10. See if that exists. There you go. Launch 10 was a Falcon 9 rocket used by NASA. And it was a success. Amazing. Now let's see if our error handling works. So what about launch 1000? There's no way SpaceX has had that many launches by now. All right, we got our 400 status and our message that says launch with that ID doesn't exist. Final step here, let's implement this route in our front end. So we now have the capability to implement this load launches function. This is going to populate this launches variable here that we use to display our historical and upcoming launches. Okay, so we'll start with a fetch to our launches collection. And remember that this defaults to the same domain that the front end is currently hosted on. So we don't need to specify localhost or an IP address here. And then we'll do something similar like for planets here. So we'll do .then launches response and return the launches response.json. And then with our fetched launches, we want to list them in order. Let's say in increasing order from lowest flight number to highest flight number. So we're going to assign our launches variable at the top scope here. And we're going to use our fetched launches using this sort function, which takes two items of that list, and based on the order of those two items, A is less than B, will determine how we sort our launches. It will determine the order of the launches in our collection. So we're going to return the increasing order. So we're going to say if A dot flight number is less than B dot flight number, we want A to go before B. And whoops, I don't want this to be under abort launch. I want this to be under load launches. Okay, let's see the fruit of our labor. Let's see the results. So we're going to rerun our API. And let's browse to our mission control dashboard. So if we refresh it, let's see what happens when we go to the history. Hey, check it out. We're getting all of our launches up to the current date. And for each launch, we have the success represented by this flag here being green versus red for failure. We have our sorted flight numbers, the date of the launch, our mission information, the name of the rocket used, and all of the customers. Very cool stuff. This makes browsing the data a lot easier. And now we can track the launches that we set for our exoplanets. I'll see you in the next one.